Hey guys, this is part two of our intro to electricity and circuits unit. We're going to dive a little bit deeper into different types of circuits, different components of circuits. So we're getting a little bit more detailed during this part two lesson here. Essential questions that will be answered during this lesson are number one, what is a circuit? How do we define a circuit? Number two, what are the four main components of a circuit? And last but not least, number three, how do we draw circuit components? So just as a quick review, I know I put this cartoon in our part one series of this lesson, but just as a review to define voltage, current, and resistance. Voltage is the difference in charge between 2 points. It's a force that causes electrons to move in a common direction. You can see here in the cartoon that the volt guy is kind of pushing the amp or the current kind of through the wire. So it's some sort of force that's pushing the electrons in a common direction. Current is the measure of the rate at which electricity is flowing. And resistance is the opposition to the flow of electrons. So again, you can see in the cartoon, the ohm is kind of lassoing the amp and trying to prevent him from moving through the wire. So it's offering some sort of resistance. Also, as a review from last week's lesson, electrons in a circuit flow from negative to positive. So you can see here, this is the symbol for a battery. We see the negative side, electrons are kind of flowing in this circuit in the clockwise direction. But current flows from the positive to negative in a circuit. When we're drawing circuits, and we're going to do this next week, you always represent the flow of current in a circuit. You never necessarily draw an arrow showing the flow of electrons, but you do always draw arrows, and you can see here on the wire the little blue arrows. You always show the direction of current flow in a circuit. So it's important to know that current flows from the positive side of a battery, for example, to the negative side of the battery in a circuit. So in this circuit, the current is flowing in the counterclockwise direction. So let's get into our lesson today. So just starting off super basic with simple circuits, there are 4 different components that need to be included in order for a circuit to work. Those 4 components are a power source, a conductor, a control, and a load. And there are many different options for these 4 different components of a circuit, but just to give some examples, an example of a power source could be a battery. This is a 9-volt battery. During our lab, we'll be using 9-volt batteries. They're perfect for what we need to do. A conductor is a wire. So there has to be some sort of wire in a circuit for the electrons to flow around and to connect all the components of a circuit into a complete closed loop. An example of a control can be a resistor. And an example of a load could be some sort of LED. Again, there are many different options for these 4 components or parts of a circuit. I would say there are less options for a conductor. For the conductor in a circuit, we always use a wire. So that's kind of easy to remember. And we'll get into some different options for these 3 components of a circuit. But before we do build or draw circuits, which we're going to be doing next week, it's important that we can define and identify common components in circuits. So all the components that we're going to go through are going to be components that we will eventually use in some sort of lab exercise. So first, a battery. We've all used batteries before. A battery is a device that stores chemical energy and converts it to electrical energy. So within a battery, there are electrochemical cells. The flow of electrons in a battery produces an electric current that can be used to do work, aka power some sort of device. Within a battery, there are a bunch of cells that are wired together to increase voltage or current capacity. Like I said before, we will be using 9-volt batteries at some point during this year. And if you actually open up a 9-volt battery, you see 6 1.5 volt cells or batteries, and those are wired together to equal that 9 volts of power within a 9-volt battery. So it's not just one big chunk, it's actually 6 1.5 volt cells that are wired together, and that equals up to 9 volts. So it's kind of cool. This would be probably a double A batteries or triple A batteries. I'm not exactly sure. We can look deeper into it, but it's interesting because we've all seen batteries of this type before. Batteries are something that we call polar. If you think of like the Earth, we have the poles, we have like south and north within the globe or within the world. But in electronics, when we talk about something being polar, we say that it has a positive terminal and a negative terminal. If you look at this kind of battery holder here, you'll notice that there are 2 wires coming off the side. Positive is always red, negative is always black. So this is going to be important to kind of memorize once we get into actually building circuits, because you don't want to kind of hook things up backwards. It can cause you some issues down the road. And we have specific names for both the positive terminal and the negative terminal. We call the positive terminal an anode, and a negative terminal is the cathode. So I won't necessarily say hook up the switch to the positive terminal of the battery. I'll say hook up a switch to the anode. And you're going to have to know that that's the positive terminal, and then that's the red wire. I have kind of a silly mnemonic for memorizing this. AP are my initials. So it's easy for me to remember because I always know that anode goes with positive, AP. If you want to use me as your way to remember this, that might be easy. So just think Miss Pastalis or Miss P, her initials are AP. So that's the anode is the positive terminal. And then, there's only one other option left. So you know that the cathode is the negative terminal. So moving on to LEDs, LED is actually an acronym. It stands for a light emitting diode. And it's a semiconductor device which allows current to flow in only one direction. So we just have a little cartoon here of an LED. Electrons in the semiconductor recombine with electron holes, releasing energy in the form of photons, light. Okay, as long as you know that the electrons flowing through the LED create some sort of light, obviously. Hopefully we've all seen an LED before. That's kind of all you need to know about an LED. LEDs are also polar. So there's a positive leg of an LED and a negative leg of an LED. If you had an LED like sitting in front of you, you'll notice that one leg of the LED is longer than the other. The long leg of an LED is the positive, or the anode, and the short leg of the LED is the negative side of the LED, or the cathode. I'll always kind of make sure you guys know this if we are going through a lab exercise, because this is hard to remember. I made these 2 legs like drastically different here so you can see the difference, but if you had an LED in front of you, it's kind of a little bit more difficult to see which leg is longer and which leg is shorter. So the long leg is the positive side, the short leg is the negative side. I memorize this because the short leg kind of looks like the negative sign or the negative symbol, but you can come up with your own mnemonic kind of for remembering this if you need that. Moving on to resistors. So a resistor is a device which offers resistance to electron flow. Pretty self-explanatory. These come in fixed values or as variable resistance units. In this picture here, we have 6 different resistors. They all have different values. You'll notice that there are kind of like bands of different colors on the resistors. There's actually a color code that you can use to determine the value of a resistor, which we'll get into next week. But just know that a resistor resists electron flow, and they come in many different values. A capacitor. Capacitor is a device that can store electrical energy. All capacitors kind of look different, but the ones that we are going to use look very similar to these. They have different values. Capacitors are made up of two metal plates, one with a net negative charge and the other with a net positive charge. So if you're looking at this picture here, this is kind of inside of a capacitor. You see the one metal plate that has the positive charge, one metal plate that has the negative charge. So those kind of charges are repelling each other. When voltage is applied over the two plates, creates an electrical field with an attractive force between them, which holds the charge of a capacitor. So essentially, if you're using a capacitor in a circuit, you can disconnect a battery, and if you still have a closed loop, your circuit can work for a certain amount of time, depending on what value capacitor you use. So it stores some sort of electrical charge that can be used if an alternate power source is not available. Potentiometer. So a potentiometer is a variable or adjustable 3-terminal resistor. There are many different styles, as you can see in the photo right here. There's ones with knobs, screws, sliders, and these can be moved to vary the resistance between the middle terminal and either one of the outer terminals, which we'll talk about in a second. So some are smaller, some are larger. Super easy to kind of see what would happen with these up at the top, because you kind of just would twist the knob and that would change the amount of resistance within that resistor. But there are also ones with like slider scales. This one is a screw, so you would have to put like a Phillips head screwdriver in there to turn or change the amount of resistance through that potentiometer. And like I said, the resistance between the two outer terminals is a fixed or constant resistance. So this very closely resembles the type of potentiometers that we'll use in class during our lab. If you hook up the two outermost terminals of our resistor within your circuit and you try to turn the knob, it's not going to change the resistance because that's fixed, that's constant. That equals the max resistance of the potentiometer. So if this is a 10,000 ohm potentiometer and you hook up both outer terminals within your circuit, it'll act as a 10,000 ohm potentiometer. Okay, even if you turn the knob, the resistance won't change. Resistance between the middle terminal and either one of the outer terminals can vary from 0 ohms to the max resistance of the potentiometer as the knob, screw, or slider is moved. Okay, so if you're using one of the outer terminals and the middle terminal and you hook those two up within your circuit, then if you turn the knob, it'll act as a variable resistor. So you can turn it all the way down and have it equal 0 ohms of resistance, or you can turn the knob all the way up. And if this was a 10,000 ohm resistor, like I said in my example before, you can move it all the way up to 10,000 ohms. Say you want to kind of move it halfway, then it would be 5,000 ohms. Again, this is just an example, and all potentiometers are rated differently, but it's kind of cool because you can manually interact with your circuit and change the amount of resistance within the circuit if you're using a potentiometer in the right way. A transistor. So transistors are kind of hard to understand, and when we get into actually working with circuits, hopefully it's a little bit more clear. A transistor is a semiconductor device which can amplify or switch an electrical signal. So as long as you know that a transistor can amplify or switch a signal, that's totally fine. You don't necessarily have to know how to hook things up or know what these kind of leads or terminals are called just yet. So when a transistor acts as an amplifier, it takes a tiny electric current at one end and produces a much bigger electric current at another end. You can just kind of think of it as a current booster, okay? So a small amount of current's going in the transistor, goes through the transistor, a larger amount of current can come out. So it's using it as an amplifier. When you're using a transistor as a switch, it can control the flow of power to another part of the circuit, turning it on and off. So instead of using a switch, like a normal switch within your circuit, you could use a transistor in its place to kind of have the same effect. Talking about switches, a switch, hopefully we've all used switches before. Switches are all over your house. Switches control the openness or closedness of an electric circuit. It controls the flow of current within a circuit. And it requires user interaction or control in order to turn on or off the switch. Many different types of switches. For our lab, we'll be using a push button switch, probably the most common, but there are toggle switches. There are also like slider switches. There's a bunch of different types of switches. You can think of like your light switch in your room. When your light switch is in one position, the circuit is open, so that means the light in your room is off. When you flip the switch, that closes the circuit, so then the light in your room can turn on. So when you think of a switch, think closed equals on, open equals off. Kind of easy to remember because open, off, they both start with O. So that can be a little bit of an easy way to remember this. So just in this kind of example here, you see when the switch is closed that the electrons can flow throughout the circuit, but when the switch is open, everything stops. When the switch is closed, the light turns on. When the switch is open, the light turns off. Photocell or a photoresistor. Photocells or photoresistors typically are called LDRs, so I might use that kind of in place of the name photocell or photoresistor. An LDR is just a light-dependent resistor. It's kind of more self-explanatory than a photocell or photoresistor, so we can call them LDRs. An LDR is a light-controlled variable resistor, meaning the value of resistance depends on how much light is shining on it. This is an example of what a photoresistor or an LDR looks like. Kind of almost looks like a solar cell, so it could be easy to remember. This is a very blown up image. They're actually super, super tiny in real life. Resistance in an LDR decreases with increasing light intensity. So you can see here in this image, when the person puts their hand over the LDR, the LED turns off. When the hand is removed, the LED turns on, okay? So there's a decrease in resistance when there's more light shining on that LDR. Decreased resistance makes electron flow easier to happen, makes current flow easier to happen, so that light will turn on. There are two different ways that circuits can be wired. The first way is in series, and the second way is in parallel. You might have already kind of gone through this in previous classes before, but I just kind of wanted to give a background so we're all on the same page. So circuits can be wired in series and parallel. Series and parallel circuits look different. Okay, they're definitely wired differently. In a series circuit, there's only one path for current flow. So you see here in this circuit, we just have a battery and 3 light bulbs. And you see that there's only one path, if you follow the arrows, for current to flow through the circuit. In a parallel circuit, there are multiple paths for current to flow. So if you're looking here and we start at the battery, we follow the arrows, once you get to this node or this part of the circuit, there becomes 2 different paths for current to flow. Current will flow through the light bulb, but also a part of the current will continue to flow through the rest of the circuit. So there's multiple paths for current to flow. Things to remember about a series circuit. In a series circuit, bulbs are equal in brightness. So if all three of these light bulbs were on, they would all be equal brightness. Each bulb receives the same amount of voltage from the power source. We call a series circuit a voltage divider. If you disconnect one bulb in a series circuit, the rest go out. I don't know if newer like Christmas or holiday lights are still wired in series, but I know I have a few older strands of holiday lights, and you'll notice that if one of the lights is like bad or crushed or broken in any way, the rest of the strand of holiday lights will go out. So that's kind of an easy way to remember this, because older style holiday lights are wired in series. And the more bulbs you add to the circuit, the less bright each bulb shines, because there's less voltage to each bulb, because the voltage, the total voltage of the battery or the power source, is being further divided. So if we needed to calculate how much voltage was going to each of these bulbs here, we would just divide the total voltage from the power source by the number of loads in the circuit, and each bulb would get 3 volts of power from the battery here, because it's a voltage divider, so it's divided equally amongst the circuit. Now talking about a parallel circuit, things to remember: in a parallel circuit, current is divided, not voltage. So something is still being divided in a parallel circuit, but it's not voltage, it's current. All the bulbs are of equal brightness and are brighter than bulbs wired in series. In a parallel circuit, equal amount of voltage runs through each bulb. And in a parallel circuit, if you disconnect one bulb, the rest will stay lit. So for example, if I disconnect this first bulb here, and I completely kind of chop that wire, closed off that wire, you still have a complete loop between bulb 2 and bulb 3 going back to the battery. So even if you disconnect one, the other 2 bulbs in this parallel circuit will stay lit. And if we're trying to determine the voltage of each LED or light bulb in this circuit, they'll all be 9 volts, because you're not dividing voltage within this circuit, you're dividing current. So there is more power getting to each bulb in this circuit, hence why they are brighter than bulbs wired in series.